Hi there, welcome to your lesson on concavity. And notice these kittens, they're always helpful. Here we have a convex kitten, here we have a concave kitten. All right, let's talk about what concavity is. This is a big idea in mathematics, so let's master this. So here is the idea of concavity. Every curve, as it goes up and down, has periods when it is concave down and periods when it is concave up. Notice when something is concave down, it looks like this. That can be represented by a teacup, and if you've turned your teacup over, we can say that's concave down. All right, how about here? Now it is concave up. So here's another teacup, and that teacup is now concave up. So easy way to remember it, concave down, concave up. A little bit more about that. Notice that there's tangent lines drawn here. So a function is concave down when all tangents lie blank the curve. All right, I hope you're thinking of the word above. All the tangents are above the curve. Another way to look at that is something we'll see in just a moment. Now, concave down. Look at the tangents. Look where they are. A function is concave. Did I say concave down? Concave up. A function is concave up when all the tangents lie below the curve. All right, concave up. Now, another way to look at this is what's happening to the tangents. And remember, tangents represent the slope. So I guess a better question is to ask what is happening to the slopes. Well, the slopes are positive, then 0, then negative. So the slope is actually decreasing over time. So that's an important thing to remember. The tangents are decreasing, or the slopes are decreasing over time, and therefore it's concave down. Okay, when the slopes are decreasing, it's concave down. And what about here? What's happening to the slopes here? Well, the slopes are increasing. They start with a negative slope, then 0, then positive. So the slopes are increasing over time. When the slopes are increasing, it is concave up. So the tangents or the slopes are increasing. Remember that key idea, and it will help you with this as it gets more complicated. All right, so look at this parabola. When is it concave up? On what domain? Well, negative infinity to positive infinity. It's always concave up. This is a upwards sitting teacup. It's always like that. So concave up from negative to positive infinity. All right, when's it concave down? Never. All right, how about this one? This parabola is never concave up, always concave down from negative infinity to positive infinity. Let's put these ideas together in this graph. We have this function going up and down, up and down. Okay, what is happening to the tangents or slopes in this zone from here to here? What is happening to the tangents? The tangents or the slopes are increasing. Okay, we have negative slope, then 0, then positive. So the slopes are increasing. And we said when the slopes are increasing, we will have a concave up parabola. And what that tells us also about the second derivative of this will be positive. So the second derivative tells us what is happening to the slope. Remember, the first derivative tells us what the slope is. The second derivative tells us what is happening to the slope. Okay, so remember that. Second derivative will tell us what is happening to the slopes, and the slopes here are increasing, so the second derivative will be positive for all values here. Therefore, concave up. Okay, look at this middle portion from this point to this point. It's clearly concave down. It's like a downward teacup. But what is happening to the tangents or the slopes? Imagine tangent lines there. What is happening to them? They are decreasing, right? We have positive tangent lines, then 0 slope, and a negative slope. So the slope values are decreasing over time here. And therefore, the second derivative will be less than 0 or negative. The second derivative will tell us what's happening to the slopes, and here the slopes are decreasing. Second derivative will be negative. And then it is concave down. Okay, last one. What's happening here? Well, it's just like the initial part. We see now it is concave up. Therefore, the tangents and slopes are increasing. The second derivative will be greater than 0, means positive, and therefore it will be concave up. So now remember this key relationship. The idea of the tangents increasing will lead to a positive second derivative, and that tells us concave up. Okay? And here, these decreasing slopes will lead to a negative second derivative. therefore concave down. Okay, I spent a lot of time on that because that's a key idea here, and if you understand that conceptually, it makes a lot of the analytical math we do much easier. So let's keep going. Okay, these points have a special name. The points where we change from one concavity to another, those are called points of inflection. Sometimes you'll see this written as inflect with an X here instead of the C and the T, inflection. Both ways are okay. Okay, now what did I just draw here? That's the derivative, okay? That's the derivative graph of this one. So notice here, right, we have negative slope, so here's negative values of derivative. Sorry, I should put derivative, there we go. Here's negative values, and then from here on, the slope is positive. So notice here, no slope here, so 0 value, and then positive slope values, positive, positive, positive. Notice that here, greater positive slope, and then here, still positive, but now decreasing positive slope, and that's what's happening here. Here's increasing slope, and then it starts decreasing, right? There's less slope here, until we get to here, 0 slope. So here, positive gets to 0, and then we have a negative slope, so here we have negative values of y, and then here, at this point again, at the point of inflection, it goes from like becoming a bigger negative slope to less negative slope. And that's what's happening here, less negative, and so on. Okay, another key idea coming at you right here. So when, notice here, okay, this is the derivative graph in blue here. There's no slope there. That means the second derivative will have no slope right there. So when the second derivative has 0 slope, that is where we have the points of inflection. And where's another place where the second derivative will have no slope? Okay, so here's the first derivative graph. Oh, it reaches a point here where the second derivative will have no slope, because the second derivative is like the tangent for the first derivative, right? So here's the first derivative graph. Here it'll have no slope. So second derivative will tell us there's no slope there. Oh, and guess what? That's where we have a point of inflection. Very important to know. All right. So to summarize what we just saw about concavity, more cats. Cats are great. Here we have concave down, sorry, concave up, and that's where the second derivative will be positive. Concave up, second derivative positive. Okay, here we have a cat that shows concave down, and when we have concave down, we know the second derivative will be less than 0, negative. So negative second derivative tells us concave down. Positive second derivative tells us concave up. Okay, let's go to Desmos and take a look at that as well, because we did something on Desmos recently that can maybe illuminate this a little bit more. So here we had a parabola graphed. Okay, we know a parabola, thinking of this in terms of concavity, this is concave up all the time for sure. Now let's think of it in terms of tangents or slopes. What's happening to the tangent lines as we follow the curve? Well, first, the tangent lines are negative, so we have negative slope, 0 slope, positive slope. So over time here, the slopes are increasing. They're going from negative to positive, so they're increasing. Slopes are increasing, therefore second derivative will be positive, therefore concave up. Let's take a look at that. Here's our initial graph. Here's first derivative. First derivative tells us about the slope of the original graph. And we can see here slope is negative, so we have negative values. Then here slope is 0, and we have value of 0. Here slope is positive, and we have positive values. Now we're going to take a second derivative. Second derivative is y equals 2. Graph that. And remember, second derivative tells us about what is happening with the slopes. And we saw again that these slopes are increasing. And the slopes are increasing at a rate of 2. That's what the second derivative tells us. It tells us the rate at which the slopes are changing. So they're increasing at a rate of 2, a positive rate, because they're increasing in a positive direction. So that's what that second derivative tells us. And therefore we see concave up, because the second derivative is a positive value all along here, so concave up. Okay, let's continue here. So we have this curve. I'm wondering, when is it concave up? You tell me, what's the interval of concave up on this graph here? Okay, let's check it. First of all, points of inflection are points where concavity changes, so you have to decide where those are. It might be kind of hard to see, but here you can see, okay, right there, concave up, and then from that moment forward, we can say it's concave down, and then again, it changes. It's hard to pick that point sometimes. Where is that point exactly? But I think you can kind of approximate where it goes from pointing down to up. All right, so now that we have those, we can say it's concave up from negative infinity to negative, I estimated this at negative 0.8. Union, so also it is concave up from this point, and I estimated that at 0.7, 0.7 all the way to infinity. All right, so when is it concave down? Well, now that we know those points, we can say it's concave down between those points. So between -8 on the x-axis and 0.7 on the x-axis. So there's our interval for concave down. And where are the points of inflection? Well, I just put them on here, and they are at -0.8, -1, and 0.71 about. Okay, now that we're feeling good about concavity and points of inflection, let's try some problems out. So let's start with this one here. We have this function. Let's find the first and second derivative to begin. Okay, here's your first derivative by the power rule and your second derivative. Now, second derivative allows us to figure out where we have points of inflection. Okay, so just like we did when we were doing the first derivative before, now we're going to take the second derivative, set it equal to 0. Because when the second derivative is equal to 0, it means it's neither concave down or up, and we have that turning point from concavity, one concavity to another. So let's set it equal to 0 and solve for x. Okay, set the second derivative equal to 0, solve, and we get an x value of 1/2. That tells us at 1/2 there is no concavity, because we have second derivative equals 0. It's neither positive nor negative, so no concavity. It's a point of inflection, and therefore we can use that point to figure out if it's concave down or up before or after that point. So remember, when we did the first derivative test, we did the same thing. We checked what happens before and after this point. We're going to do the same thing here. What's an x value before 1/2? Well, an x value before 1/2 is 0. So put 0 into the second derivative, which is here, and do you get a positive or negative value? Well, we get a negative value. That tells us before this point, it is concave down, because the second derivative is negative, so it's concave down before then. Okay, how about trying out x value after 1/2? So let's say a 1. So we put a 1 into the second derivative. All right, do you get positive or negative? You get positive. That means after this location, it is concave up, because the second derivative, whether we get positive or negative, tells us about if a graph is concave up or concave down. Okay, therefore, it is concave down when? From -infinity to 1/2, and it is concave up when? From 1/2 to positive infinity. And what's the inflection point? It is this point. But what's the y value? Put it in the original. What do you get? Okay, 1/2, and what y value is that? I don't even know. I don't have it. I hope you figured it out. That value, that half goes in here, and you can get it. Okay, let's try another one. Try this one, x cubed. Do the same thing. Find the intervals of concavity and the points of inflection. Okay, check your work here. So here's first derivative, second derivative. Set the second derivative equal to 0, and we get an answer of 0. So 0 must be a point of inflection. Okay, so we check a point before x equals 0, x equals -1. Put in the second derivative, we get negative. Take a value greater than x equals 0, maybe 1. Put it in the derivative, second derivative, we get positive. So this thing, by the way, is called a sign chart. It's another way of doing what we've been doing here. You check values before 0, you check values after 0, and you figure out the sign. Okay, negative, positive. Same thing we've been doing here. So that tells us it's concave down from -infinity to 0, and concave up here when you're 0 to infinity. And the point of inflection is 0, 0. It's that point, but if you put 0 back in the original, you get 0, 0, 0. Okay, let's try one more. This one, we have, I have your function, I have the first derivative. I've done it for you to save you some time, because this requires quotient rule. But now you're going to find the second derivative using quotient rule again. So try it out. Do quotient rule on that, get the second derivative, and then see if you can follow the same steps we did. Setting it equals 0, finding points of inflection, and so on. Let's see how it goes. Okay, check your work here very carefully. Here's that. Here's the first derivative. Here's the second derivative. Wow, lots of work there. Hopefully you figured it out. Set the second derivative equal to 0, so all of that equal to 0. Solve, solve, solve. You get to this point here where you can't solve that. You can't take a square root of a negative, so no real solutions right here. However, and you may remember this from before, we have these things called critical points. We can find them when the derivative is equal to 0 or when the second derivative is undefined. We did that for first derivative. It's undefined when the denominator is 0. So we set it equals 0, we get two answers. Now those are our critical points. We test values around those, negative, positive, negative, and it allows us to find concavity. Great job.